Well, good morning. So, I can't call 89 students. That would have been ridiculous, but I guess I can call a dozen. So, Miss Lauren Banks. Sorry for wrong pronunciation. Yunting Chen. Miss Stephanie Chung. Miss Catherine Kane. All right. You don't like following instructions, are you a rebel? Miss Damian Clement.
Thank you.
Yongyan Ann. Minwei Kelly Ryan. Daria Listkova. Daphne Lloyd. Veronica Lynn. Devian Howe. Brian, that's W or U? See? Brian, any Brian. Catherine Kane. Young Halran. All right. Once in a while, it's worthwhile. So, this is our current topics, and the goal today is to finish it, start new topic, and finish it as well. So we could concentrate tomorrow and on Thursday just more on problem-solving strategies. A question: it's a summertime. You want to make ice cubes for your drinks, and you pour certain amount of water into ice tray. The water taken from room temperature, 25 degrees of Celsius. You pour it in ice tray, place it into the freezer, and the question is, what should happen to the heat? Should it be absorbed or released in this particular situation? So, please take a minute, check the Weber sign, and of course, in physics, we start from a picture. Well, we just call it a diagram, and in this situation, we start from a certain amount of water. Well, water looks like a puddle to me, so something like this. And an ice cube looks like a cube to me. So something like this. We can see the difference. Liquid state, a solid state, and we know that water initially has a certain temperature, which is 25 degrees of Celsius, and we know that eventually we're going to have ice cubes at -5 degrees of Celsius. So we can think of the process which should be used, well, we call it cooling down. And for that particular process, we can write an equation which relates the amount of heat, the specific heat, the mass, and the temperature change. In Kelvin or in Celsius, doesn't matter. And now we can actually plug the numbers. 4,000 in joules per kilogram Kelvin, so I have to use international system of units. What is the mass? Well, we have 20 cubes, 5 grams each. And the temperature we know always final, minus initial. I just realized I have no coffee to walk. All right, I'm going to just walk. Coffee or no coffee, if I'm walking back and forth, what does it usually mean? You discuss it.
I think not only, but also the phase change.
Yes, we all have our phases. My phase was making a mistake. Now I'm changing to a different phase, fixing it. Because of course, if we go from a liquid state to a solid state, it has to be phase change, and this equation doesn't account for the phase change. So what should I write? There's one word. Starts from W. Wrong. In physics, everybody has only 3 phases or stages. We know we're right, we know we're wrong, and we know we don't have enough information to make a judgment. That's it. So we know we are wrong. You are absolutely correct. However, still, this reasoning helps to understand if the heat is being absorbed or released, because even if we look at this wrong equation, still it gives a negative value for Q, and negative means it should be, let's check what people say. That's a question number 2. Released, yes. Well, this is an easy fix, of course. I just need to add an extra slide, so I don't want to erase this. Sometimes knowing what's wrong is even more important than doing it right. So we start from a certain amount of liquid water, and we have to cool it down from 25 degrees of Celsius to what? What is the lowest temperature? 0? It cannot be liquid below 0. Now it starts freezing, and this process happens at 0 temperature. And after that, we left with solid water, which we call ice, but we're still taking away energy from it. So it's cooling down from 0 to -5 degrees. So this situation describes the general strategy. We have to list all objects, for each object, all processes, and we only have two processes to choose from: temperature change or phase change when temperature remains constant. And then for each process, we should write the expression for the amount of heat associated with that process. That's it. And in this situation, so we can assign Q1, Q2, Q3 for each process. Q1 should be equal to specific heat of water times mass of water times, for this process final temperature is 0, but initial was 25. And for water that will be equal to 4,000 kilograms, joules per kilogram, Kelvin. Again, 20 ice cubes, each weighs 5 grams, which is 0.005 of a kilogram, times 25, and a minus. That's going to be joules. Bless you. Q2. Now, that amount of heat is related to phase change. So, a different expression. And what's missing? What should I write? What should I write? Something is still wrong. What is wrong? How do we fix it? What is wrong and how do we fix it? Someone has to say something. It's related to your answer to this question. It has to be negative, so how do we fix it? Yes, with a negative sign or a minus. And it has to be done manually. And then the third Q, of course, now it should be specific heat of ice times, well, that's the same amount of material, yeah, same mass, but now final temperature is -5 and initial was 0. For ice, specific heat is about 2,000, 20 ice cubes. For each ice cube, the mass is 5 grams, and that's going to be -5 joules. This is negative 300,000 times same mass, 20 ice cubes, 0.005 joules. And the total amount is just equal the sum of three terms. Should it be equal to 0? No. It's not a thermal equilibrium problem. It's a state change problem or temperature change problem. It's not inside of insulating system. It's inside of a freezer, which running and takes energy away from it. Any questions? Yes? L, capital L, latent heat fusion. I think I have values here, yeah. This is how much heat should we, for example, spend to melt 1 kilogram of ice completely. Well, we have 3 Qs, so you should check all of them. For each process, we have a certain amount of heat associated with it. If it's a temperature change, we have to use Cm delta T. If it's a phase change, we have to use L times M. And since we only have two choices, it's kind of pretty straightforward. If you look at the diagram, temperature changes, Q equals Cm delta T. Temperature doesn't change, Q equals plus or minus L times M. And next problem is on the thermal equilibrium. So what is happening here? We have, well, normally that would, if in a lab setup, that would have been a piece of lead, a solid object, placed in liquid, normally would have been water. And in maybe styrofoam bucket, so there is no heat exchange with the surrounding. So eventually they reach thermal equilibrium, and we see some relationships in words. And the first step, of course, is to write those relationships mathematically. So again, we start from a diagram, and well, no, first we start from a picture, because I have to read everything to relate these temperatures and et cetera, et cetera. So this is a piece of liquid and a piece of solid, and so liquid has initial temperature of 500 degrees of Celsius, and the solid object twice of that. So initial temperature of liquid, initial temperature of solid, that's going to be 1000 degrees of Celsius. And they have masses, because everything does. And the solid object has mass of 1/3 of the mass of this liquid. Okay. They have specific heat each. And the specific heat, well, it has the masses, but it's solid. Specific heat is twice of the specific heat of the liquid. Oh, the container has the mass. So there's a box, the third object. Okay. And the box has the mass, which is equal to 1/4 of the mass of the solid object. Okay. And the specific heat of the box is equal to 1/2 of the specific heat of the liquid. So they're all involved in the heat exchange, and they all eventually reach the same temperature. Now, nothing is said explicitly about the initial temperature of the box. So we have to make a natural assumption about it. Any suggestions? Please. That is natural, but there is more natural. It holds water or liquid inside it. So they've been sitting. You don't pour water in it, you know. If you had the box sitting on a tabletop and then you pour in hot water in it, probably initially they would have different temperature. But if the box was sitting with water together for a long time, the natural assumption is they have reached the thermal equilibrium between themselves. So the box and water have the same temperature initially, and then we're adding a hotter solid. So it doesn't matter, of course. The number doesn't matter. It doesn't affect the strategy. But now we know all the temperatures, and now we can draw the diagram, because I like to show an object with a higher temperature at a higher place in a diagram. So the hottest of these three objects is the solid, and the box and the liquid, they initially start from the same temperature, and in time, hot things get cooler, but cool things get hotter, and eventually they reach the same final temperature. Let's call it lowercase. Let's use Celsius for everything. That's it. So now we can see how many processes happening. We have to assume no phase change happens because we have no information on latent heat. And now we just have to write 3 times the amount of heat we need to associate with each process. And the equation for each process is the same because it's a temperature change, so it has to be equal to, well, let's call them liquid, the temperature change of the liquid. Easy fix. This is solid, temperature change for the solid object, liquid, temperature change for the liquid object, and box, temperature change for the box. But now we have to make one additional step relative to the problem we just previously solved. Here we just had to add all Q's. In this problem, because there is no heat exchange with the surrounding, we have to set that sum to a specific number, which is what? 0. So this is what we need to write. Qs plus QL plus QB equals 0. All right, so evidently I need to add an extra slide. So QS plus QL plus QB equals 0, or CS MS delta TS plus CL ML delta TL plus CB MB delta TB equals 0. All right, now we have to read our relationships. So solid object has specific heat twice than liquid and mass 1/3 of that. So twice times specific heat of the liquid, 1/3 times the mass of the liquid times final temperature minus 1000 plus, well, I keep all variables for liquid the same. And now it should be same final temperature minus 500 plus, what do we know about the box? It has specific heat a half of what liquid has, 1/2 times the mass of the box is 1/4 of the mass of the solid. One quarter of the mass of the solid, but the mass of the solid is 1/3 of the mass of the liquid times final temperature minus 500. Well, and this has to be equal to 0. We just have to follow this strategy step by step and using connections given to us. And now we can see that we can cancel lots of things. And now the equation has, well, I will write it. 0 equals 2 over 3 final temperature minus 1000 plus final temperature minus 500 plus 1 over 24 final temperature minus 500. And that should do it. Physics is done. Now we have to open all the parentheses, multiply everything, collect the final temperature on one side, and solve it. Solve for final. That's a good exercise. And later on, I will add the slide so we could compare the numbers, but I'm going to do it on my own, and you have to do it on your own. And we're done with thermal equilibrium. And now we are moving on to properties of gases. If you have no questions. Well, the first thing we know about gases, they're made of molecules or atoms, and those particles are tiny, and we always have a huge amount of them, even in a very small volume. So using international system of units, using kilograms or even grams, not really convenient. For example, here you can see a number for the atomic mass of oxygen, -26. We have no intuition on that. And if we take a certain amount of any gas or any matter for that matter, the number of molecules is huge, 10 to the 22nd, 23rd, 24th, 25th. So in order to deal with numbers like that, people, chemists actually, have invented an additional unit. They call it a mole. And by definition, it's a specific amount of matter which has a specific number of particles. This number, 6.02 times 10 to the 23rd, this number was named for the physicist Avogadro, so it's an Avogadro number. And any amount of matter which has this number of particles called 1 mole. That's it. So if we know how many particles in certain amount of, we can calculate how many moles in it. If we know the molar or atomic mass of a single particle, we can calculate the mass of a single mole of that material. We just have to multiply two numbers. Well, if you've taken chemistry, and most people take chemistry before physics, and I don't know why, that's wrong. You should know all this stuff. So this is an official definition of what we call the number of moles. Yeah? What do we do? Well, we have to count how many particles is inside a specific container, and then we have to calculate the ratio of that actual number of particles divided by the Avogadro's number. That will be the number of moles. However, of course, it's really, really hard, inconvenient, trying to count the number of particles. It's huge. So what do? Well, we switch to more measurable variable mass. And we can multiply by atomic or molecular mass, numerator and denominator. And this will give us just the mass of that sample. Yeah? If we take this sample of material, put it on a scale, that's what we read. And this is the mass of a single mole or molar mass. And historically, there are two different letters, symbols people use almost equally frequently for the mass of a mole, molar mass, capital M or a Greek letter mu. So it doesn't really matter. And molar mass, of course, has been measured for all elements. And this is just a copy of a periodic table which you have on each wall. And the question to you, if you look at the periodic table, what answer should you choose for the mass of 1 mole of hydrogen? You shouldn't be looking at this, probably. You should be looking at the periodic table on the wall. It's larger. But hydrogen is the first element in the table. First, number 1. And in its normal state, it's a diatomic gas. The molecule is made of 2 atoms. So it looks like this. 1 atom of hydrogen, second, they bonded, that's a molecule. And I'm going to check your answers. And here it says, that's the question number 3. And we already have splitting almost 50-50 between answer 1 and answer 2, and also some none of the above. Okay. If you chose first answer, please raise your hand. Well, someone has to, because I saw several people. Okay. Don't be shy. If you chose second, please raise your hand. Okay. Now, this is a hint. If you didn't use the hint, that's why you chose 1 or 2. If you chose 1, you thought of atomic hydrogen, which happens at very high temperatures. But a molecular hydrogen, H2, has 2 atoms. And for each atom, there's mass associated with it. So we have to take that mass, multiply by 2, and the periodic table gives us the molar mass, well, 2 times 1, in grams per mole. But all answers have been provided in kilograms. So the right answer is none of the above. Pay attention to units. That's what it means. Pay attention to units. So the molar mass of the hydrogen gas is 2 grams per mole, or 0.002 kilograms per mole. But we usually read it differently. If we take 1 mole of hydrogen, if place it on a scale, we read 2 grams. Well, this is just a review. Now, an ideal gas, by definition, is composed of particles which don't interact. We neglect any interaction. They travel chaotically in all directions. They might collide, but if they collide, then bounce off each other, experiencing absolutely elastic collision. So there is no energy loss. There is no internal friction. And the question number 4 for you, if you would be able to measure velocity of each individual particle and then add them up together and then divide by the number of particles, because that's how we calculate the average in mathematics, what would be the average value for the velocity of each particle in this gas? And let's see if this works. All right, I'm going to switch. Okay. So this is a simple model of a gas with many different atoms and molecules, heavy, light, and the wiggling represents the temperature. This is a really high temperature, and I can cool it down. So they travel slower and slower, less and less kinetic energy. Well, this represents 0 temperature if I use absolute scale. Everything freezing. Well, according to quantum world, there has to be some fluctuations, but this is a classical world. In the classical world, at 0 temperature in Kelvin, everything freezes, nothing is moving. So that's why in my question, the temperature was set slightly above, or maybe greatly above. Doesn't really matter. So, as you could see in this experiment, some particles travel to the left, some particles travel to the right, up or down. So they travel chaotically in all possible directions. And because of that, if you add, I should have it here, yeah. If you add vectors and if you add numbers, the results must be different. In this equation, we are calculating the average kinetic energy. So each particle, like a tiny ball, flies in space, and it has instantaneous speed. mv²/2 represents kinetic energy. And for each particle, there is a specific amount of kinetic energy. It changes when they collide, of course, but still, kinetic energy is never 0 if temperature is above 0. And if we add all positive numbers, the number is positive. And if we divide by a positive number, the number is positive. Kinetic energy cannot be negative. So kinetic energy is 0 when absolute temperature is 0, or positive. But the question wasn't about energy. The question was about velocity. And velocity is a vector. And we have to add all vectors together. And if you look at this picture, for each arrow in one direction, there is an arrow in opposite direction with the same magnitude. And how do we add vectors? Tail to a head rule. So they all have to cancel each other out. And the average velocity of all molecules in the gas is 0 because it is not moving. Inside this ball here, on average, there is no flow of air in any direction. To make it flow, we would have to, what do we have to do? We have to generate pressure difference. Have to blow, use a pump. In that case, they all will travel with, well, average velocity in a certain direction. And by the way, how do particles exert the pressure? By just knocking on the surface. When they hit the surface, surface hits back, and the number of collision per second over square meter is related to the force. Force over area gives pressure, and the pressure is the result of collision between particles and surfaces. That's it. And if particles travel faster, so they collide with the wall more times per second, higher pressure. If particle travels slower, so there is lower number of collisions, lower pressure. If they don't travel at all, freeze, pressure is 0. Yeah. So there has to be a connection between how they travel, fast or slow, and the pressure, which means has to be connection between energy and the pressure, kinetic energy and the pressure. High kinetic energy, high pressure, low kinetic energy, low pressure. And by the way, we can use this picture to go back in time to kind of explain why when a fluid travels faster, it exerts lower pressure, because when it travels slower, it collides with the surface many, many times. When it travels faster, it doesn't exert so many collisions anymore, so less pressure. Well, so how do we relate kinetic energy and pressure? First of all, we introduce a new physical quantity, temperature. This expression is an official definition of absolute temperature. So what do we need to do to measure or calculate temperature in Kelvin? First, we have to calculate kinetic energy of each particle. We have to add them up. We have to divide by the number of particles. That will give us average kinetic energy. And then we'll have to multiply that number by 2, divide by 3, and divide by a fixed constant, which has a name, Boltzmann's constant. And if we do that, the resulting number has a name, absolute temperature of that system. Of course, after giving that definition, we have managed to measure the temperature, so we don't have to do all that exact calculation. We do it backwards now. We can measure temperature, and using that equation, we can calculate the kinetic energy, average kinetic energy. Even more specifically, average translational kinetic energy. Because we know that all objects also could rotate. So translational kinetic energy means kinetic energy of a center mass. It travels, remember center mass, a special point, it travels in space, it has specific speed. So mv squared over 2, that's translational kinetic energy. Now, there is a different approach, theoretical, to relate pressure and energy. Because each particle hits the wall, and the wall hits back. We know that the force exerted from a particle on the wall has the same magnitude as the force exerted from a wall on a particle. And we can apply the Newton's second law to relate force and change in the momentum. And then there is a simple model and simple algebra, which brings from Newton's second law to Gauss' law of kinetic theory. Kinetic theory relates pressure, well, the volume of the container, and average translational kinetic energy. Now, this exercise, for example, I've done when I was in 10th grade. From here to here. It's not a very complicated model. It relates one equation with another equation using some algebraical manipulations. We don't have to do that. You can. Yes, you can. But you don't have to. What we have now is an equation which has been derived from Newton's second law, applied to molecules flying and colliding with walls, and a second equation which is a definition of absolute temperature. But if we have two equations, we can merge them. This merged with that, and now we have an equation which relates the pressure inside a certain container, the volume of that container, and the absolute temperature. However, we don't like using this equation normally because this constant, Boltzmann's constant, has a very weird power. So, plus this variable represents the actual number of particles, which again is a very weird number. So we make a transition from the actual number of particles to the number of moles, because that's much easier to count. 1 mole, 2 moles, 3 moles. But in that case, we have to switch to a different constant. We call it a universal gas constant, which is equal to 8.31, which is again very natural number to us. And the ideal gas law describes all processes with all ideal gases. That's it. Basically, we are almost finished the whole theory. We just need to talk about energy change and the work. But I think I'm going to do it today as well. So the summary. The question. This is the ideal gas law for any gas in a container at a certain temperature. We always can relate the pressure inside that container, the volume of that container, the absolute temperature of the gas at absolute temperature, capital T, the number of moles, the amount of gas, and we also have a constant 8.31. And for example, if I will calculate this ratio, and to do that, all I have to do just divide both sides of the gas law by constant and temperature. Constant and temperature getting canceled. What's left is N. That's not what I want to do. I want to do this. I want to divide product of pressure and volume over number of moles and temperature. In that case, the answer is R. And that is definitely a constant, 8.31. So no matter what is happening to gas, no matter if we expand it, contract it, heat it up, cooling down, poke a hole, so some gas getting lost, this ratio, pressure times volumes over the amount of moles times temperature, always remains the same. But this, well, if we use this equation, the result is N times R. And what does N represent? Amount of gas. Is it always the same? Is it always constant? The R is constant. That's why it's always constant. But how do I change the amount of air in this balloon? Like this. If I change the amount of gas, Newton's third law, if I change the amount of gas, this variable may change, may. So this ratio is not always constant, and it's not always change. Sometimes it is, sometimes it's not. We have to pay attention. Well, now we have to solve an example. This is a situation similar to my experiment with the balloon. An ideal gas has a certain temperature, and what do we do with it? We change pressure. We let some portion of the gas out. We change the volume, and we need to calculate the final temperature. So the key word is change, which means we have initial state of the system and the final state of the system. And for each state, we can write the same law. PV equals nRT. PV equals nRT. But since we have two different states, we have to mark, label each variable. Initial. Do I have to label R? No, it's constant. Final. All right. Now we need to start reading and transferring every verbal relationship into mathematical relationship. Well, what do we know? Ideal gas has initial temperature of 127 degrees of Celsius. This is what we're looking for, the final temperature. The volume was tripled, so final volume is equal to 3 times initial. The pressure was decreased to the half of the initial. The final pressure equals a half of the initial. And a quarter of the gas was lost. I miss my coffee. Someone has to say something. Or we will have to continue more theory tomorrow, which is really, really good for me. The key word is lost. Yes? The mass? What do you mean by mass? I don't see any mass here so far. The pressure was decreased to the half of the initial. So that's fine. I had initial pressure and I decreased it to a half of the initial. The volume was tripled. So where else should we check? Yes, you moved and you changed your place, so Again, the key word is lost. The equation doesn't use any information to anything what lost. It's lost. It's gone. It went away. The equation has to be related to what's left. Yes? So, what is the word I have to write? Starts from W. Wrong. But there's an easy fix. The final amount of gas should be equal to the initial minus the amount of which was lost. It's lost. It's out. So what's left is important. That's 3/4. Well, now, all I have to do is, well, actually, what I like to do is just write a ratio. P initial, V initial over P final, V final should be equal to N initial, R T initial over N final, R T final. Hence, P initial, V initial over. Now we can replace each final value with correspondent expression in terms of the initial value. Pressure final equals 1/2 of the initial. Final volume equals 3 times the initial. Equals. Okay, let's keep constant for the moment. Final amount in moles equals 3/4 of initial, same constant. And final temperature is what we're looking for. Now start canceling. Pressure, volume, number of moles, constant. So 2 over 3 would be equal to 4 over 3 times initial over final. I can cancel 3's, and that gives me T final will be equal to 2 times T initial. All right, I have to do it. T final equals 2 times T initial equals 2 times $1.27. 254. Where else did I do wrong? Yes? Absolutely right. But I'm not the only one. People do it all the time. So don't do that. Right. Wrong. The capital T requires using Kelvin. Kelvin. So first we need to convert the initial temperature from Celsius to Kelvin. And now we can calculate the final temperature. And now we can calculate the final temperature in Celsius. Six, 527. Again, pay attention to units. Any questions, please? It's a very straightforward but common situation when we have to use the ideal gas law to relate initial state and final state of a gas. This is the most complicated situation when everything changed. Pressure, volume, amount of gas, temperature. But it doesn't happen very often. Usually something remains constant. And we have 3 standard processes. And I'm just going to show it very quickly. This takes all the budget of physics department. All right, so let's pour some hot water in it. This is called pressure bulb. It looks like a bulb. What's going to happen? Okay, you see only this, so you have to look, you use 2 eyes, look at this and at that. When we immerse the bulb in hot water, it starts moving slowly, but it's moving. The pressure increases. What kind of a process is it? Temperature changes, pressure changes, but the volume of this bulb remains constant. A process like that has a name, isochoric. Of course, I can cool it down, put into ice, and in that case, now the temperature drops. Well, we see pressure, but when the volume remains constant, when pressure increases, temperature increases. When pressure drops, temperature drops. And this is how people can use a device like that to measure temperature. Just put it in hot water, write 100, in iced water, write 0, and measure temperature in Celsius. Second process. Well, if I press the piston in a syringe, I can see the pressure changes. But if I do it very, very slowly, the temperature in the system remains room temperature, which means constant. So this process at constant temperature has a name, isothermal. And what we can see, when I keep pressing, I decrease the volume, pressure increases. But if I release the piston, the volume increases, the pressure decreases. So they're inversely proportional. But the product, pressure and volume, should remain constant. And one more process. Well, first of all, this is an example of, we're going to talk about how can it do work. I can compress this bottle, and the air pushes on the piston and does mechanical work when height changes. MGH, mechanical work is done. So we lift it. But we can do exactly the same work by using, well, hopefully hot enough. Yep. So what's happening? The temperature increases of the gas, and the volume should also increase, but the piston balanced out by the force of gravity, and the force of gravity is constant, so the piston is balanced by the same force, so the pressure being maintained the same inside, and this process has a name, isobaric process, and also this is an example of a mechanical engine. Of course, now I have to cool it down, and then I can warm it up again and cool it down, and it will repeat itself. And I attach to a wheel and make it work. So, 3 standard processes, and we need to know names because sometimes it's used in a problem. It says isobaric. We need to know it means the pressure remains constant, for example. These are the graphs. These graphs have a name, a PV diagram. It describes what is happening to the pressure as a function of volume. When pressure is constant, of course, it doesn't change. This is the graph for the isochoric process. Pressure changes, but the volume is constant. And this is the graph for the isothermal process. Increasing volume, decreasing pressure. Going back, decreasing volume, increasing pressure. Well, now we need to know how to calculate the total energy of the gas, and the name for that total energy is internal because it's inside it. Internal energy, of course, is based on the energy of molecules. If we start from a single gas made of molecules, which made of a single atom, like helium, we call it a monatomic gas. Those molecules only travel in space, so they only have translational kinetic energy. And if we know energy of a single molecule and multiply by the number of molecules, that gives the total energy of the whole gas, or we call it internal energy. And so the internal energy, a standard letter for internal energy of the gas is U. However, sometimes it might be confusing because we used to use the same letter for potential energy. Well, it's a different situation, different system. Same letter, different meaning. And a definition is the product of the total number of particles, well, in this case, atoms, times the average value of translational kinetic energy, and according to the definition of absolute temperature, this is how we should relate them. What happened here? But we can make a transition again from using the Boltzmann constant to using the universal gas constant. Remember, the ideal gas law has two different forms. And what we see in this expression for the internal energy is the initial form of the ideal gas law. But now we can just replace this product, number of particles, Boltzmann constant, and absolute temperature, with this product, the number of moles, the universal gas constant, and the same temperature. So this is how we can calculate the internal energy of a monatomic gas. However, because number of moles times constant times temperature also equals PV, pressure times volume, this is another expression for the internal energy. Which do we have to use? We don't know. When we need to solve a problem, until we solve a problem, we don't know how to solve it. We have to try different strategies. So we can start from this. It doesn't work. We can try, switch to this, and see whichever gives the answer. That's the only way to do it. So the summary for the monatomic gas. Now, the difference between a monatomic gas like helium, diatomic gas like hydrogen, oxygen, nitrogen, is that when a molecule is composed of two atoms, in addition to translational motion of a center of mass, it also can rotate about the center of mass. And rotational kinetic energy should be included into the total energy. That's it. So to include rotational kinetic energy, we just have to count how many independent rotations we can observe. So for a diatomic gas, when it spins like this, it requires some energy. When it spins like that, it requires some energy. But if it spins like that, it doesn't require any energy. Of course, we see the ball. The actual atom is tiny. So the actual atom looks, if we look from this side, just like a line. So there is no rotational energy about the axis which goes through the atoms. And it doesn't have to be, of course, symmetrical, doesn't matter. Still, when it spins about this axis, energy is not zero. When it spins about this axis, not zero. But the third axis doesn't require any energy. And CO2, H2O, molecules which made of 3 atoms or more, in that case, they travel in space, and also they can rotate about any of 3 independent axes, X, Y, Z. So to describe total energy, we need to add kinetic energy of translational motion plus kinetic energy of rotational motion. And for diatomic gas, we have 3 from translational plus 2 from rotational. 5 elements of energy. For triatomic, quarteratomic, or any polyatomic gas, we have 6 portions of energy, 3 because of translational motion and 3 because of rotational motion. To combine all these expressions together, people have invented a new physical variable. They call it the number of degrees of freedom. For a monatomic gas, it's 3, because to describe the motion of an atom, we just need to know how it moves about 3 different axes, X, Y, Z, no rotation. For a diatomic gas, we have to add 2 more degrees to describe how it rotates about 2 additional independent axes. And for polyatomic gas, we have to add 3, well, we have 3 translational degrees, plus we have to add 3 rotational to describe rotation about 3 independent axes. And these equations combined together all expressions for all gases. The number I depends on the type of the gas. And as we said, we can also use the ideal gas law to write the same expression in terms of pressure and volume. This product, the number of moles times constant time temperature, is literally equal to pressure times volume due to the ideal gas law. That's it. So again, we have many expressions we can use. I just did it because ideal gas law relates pressure, volume, number of moles, universal gas constant, and temperature. We have another expression for actual value of the internal energy. Now, if temperature changes, the internal energy changes for sure, assuming the amount of gas remains constant, N is constant. But this expression is more convenient to use when we know that something remains constant. For example, if pressure is constant and volume changes, we can easily calculate change in the internal energy. If volume remains constant and pressure changes again, we're going to do some examples like that. So the summary, the same processes. Now, for each process, we also can write an additional expression, how internal energy changes. It doesn't change for the isothermal process, remains constant, but for isochoric or isobaric process, it changes. Do the homework. You know how to do it now. And I'm going to do it tomorrow. I'm going to skip this. I'm going to skip that. I want to mention the last theoretical part. If we have a gas in a system, how can we change the internal energy? Well, first of all, we can place it into hot water. And that's what we call heat exchange. But also, we can do some work on it, mechanical work. And we can do it together. Well, of course, I wouldn't put my hand into hot water and press, but you can imagine it's happening. So in that case, internal energy changes simultaneously due to heat exchange and due to mechanical work. So if we do work on the system and also bring it into a contact with additional objects, the change in the internal energy is equal to the sum between the amount of heat it absorbs or releases and amount of work done on the system. But this equation is not very convenient to use because this is work related to the external object, my hand, and the heat and internal energy related to the system, the gas. So what do? We use the Newton's third law. The work done on the system has the same magnitude but opposite sign if we relate it to the work done by the system. So we rewrite the law differently. Here in this equation, all three variables related to the system. This is the amount of heat the system absorbs or releases. This is the change in the internal energy of that system. And this is the work system does on the objects outside of it. For example, if the piston in this picture moves away to the right, gas does positive work, expands and pushes. And this equation has a name, the first law of thermodynamics. Now, we know how to calculate almost everything. Let's just mention how to calculate work. So we start from a simple process when pressure remains constant. And it's just convenient to think of a cylinder with the gas inside pushing on the piston. If pressure remains constant, hence the force, which is equal pressure times area, also remains constant. What's good about that? We know how to calculate work done by constant force. The work done by constant force is equal to the magnitude of the force times displacement, well, times cosine of the angle between the force and displacement. In my example, if the gas pushes to the right on the piston, this is the displacement. Force points to the right, displacement points to the right, the angle is 0, and the force is equal to pressure times area, and area times displacement will be equal to the change in the volume of the system. That's it. So the work will be equal to pressure times change in the volume if pressure remains constant. What if it's not? Well, we are not scared. We know what to do. In that case, we use graphic. graphical approach, graphs. For a constant pressure process, this area, pressure, which is the height of this rectangle times change in the volume, which is the base, equal to the work done. If we have a process when pressure changes, we can always imagine that it is a combination of large amount of tiny processes. For each process, pressure practically constant. We add them up, work done for each individual process, and the result is this area. So the most important fact from this slide, we can always calculate work done by gas on a system if we sketch a graph of the pressure as a function of the volume. Now, when the volume increases, delta V change is positive, so work is positive. The gas does positive work on the objects outside of it. But when the volume decreases, we compress the gas. We do positive work, so the gas will be doing negative work. And now we know everything. We know how to calculate change in the internal energy, or we know how to calculate internal energy, period. We know how to calculate work. We know how to calculate heat. We know how those variables are related. Now we can start, since we have some time left, now we can start doing some examples. Calculate the internal energy and the pressure of 1 kilogram of a hydrogen gas at the room temperature. Well, room temperature is about 20 degrees of Celsius, plus or minus, but we cannot use Celsius, so we have to add 273. The volume, 1 liter. Anybody? In meters per cubic, in cubic meters? 1,000th of it. We can fit 1,000 liters in 1 cubic meter, so 10 to the negative third. And now we can immediately calculate pressure, for example, because the ideal gas law says, we need to know the amount of moles. So the amount of moles should be equal to the mass of the gas divided by the molar mass. And this is 1 kilogram. And the molar mass is what? You look at the periodic table. It's the first element, but it's a diatomic gas, so you write 2. But, you know, if you use that number, it should be grams per mole. So you have kilograms and grams together. You have two options. You can convert kilograms into grams and cancel them out, or you can convert grams into kilograms and cancel them out. So that's easier for me, converting kilograms into grams over 2 grams, mole, 500 moles. So now, if we are looking for pressure, that has to be equal to 500 times about 8.31, wherever 8 is fine for us, times temperature, which is 293, divided by, where's the volume? Here, 10 to the negative 3. That's got to be a huge number, actually. Well, 1 kilogram, huge number of moles. And so, well, you can finish. That's going to be pascals. Now, second question is calculating the actual amount of joules stored in this system, internal energy, U. Well, it's a diatomic gas. We don't have to remember because normally you always can ask, but hydrogen is very known. So diatomic, for the diatomic gas, the number of degrees of freedom is 5. I equals 5. 5 over 2 times. Well, we can use nRT again because we know all values. 5 over 2, 500 moles, 8,293 joules. Done. Please tell me, what do you think? That's the last question for you for today. We have hydrogen stored in a container, in a vessel, and we let it expand at constant temperature. What do you think about the change happened to the internal energy of this gas? So pick a choice. I'm going to switch to the web assign. Pick your choice. Survey says. Well, I'm going to switch back for a second because it takes time to process. So you still have about 30 seconds to watch this slide to choose your answer. And actually, I want to just ask you, if you think the internal energy changes, it increases, so change is positive, please raise your hand. If you think the internal energy decreases, change is negative, please raise your hand. That's the question number 6, right? Well, I see all possible answers. Why did you raise your hand? You should have. Well, it's about picking the right equation. Let's say you picked this equation. This is an isothermal process, which means pressure and volume change both. And when you have two changing variables, you cannot predict what will happen to the product. But you don't have to, because there's a different equation which tells you that if you do not change the amount of gas, if the number of moles remains constant and temperature remains constant, the internal energy remains constant, which means there is no change. Well, okay. Let's stop here for today. I'll pick it up. We will solve this problem tomorrow. And basically, all we have to do is more problems. Thank you. I don't know. I'm first.
I have to do my first test, probably at the beginning of class. I just was Thank you. Thank you.
Sorry. Bye. I just had one question. I think I stepped out when you were explaining this. For the